How do you determine reaction rate? Typically, when we do these things in the lab, we run the reaction at a constant temperature, okay? To make things simple, we want to minimize the variables when we're making measurements. So when we're measuring reaction rates, we generally maintain a constant temperature. We monitor the concentration of a reactant or product versus time, okay? So we look at the concentration. If R is a reactant, then the rate of consumption of your reactant R is given by this expression right here. This is called a derivative, okay? Negative dr over dt, okay? And the average rate is negative delta R over delta T. What does delta mean? Change, right? Change in concentration divided by the amount of time that's elapsed. Change in time. That's your average rate. Now you put a negative value in front here. Why? A negative sign. Because delta R, if R is a reactant, what will happen to R as the reaction progresses? It's going to be dropping, right? So delta R is going to be negative. So if we want a rate of consumption, we just want the absolute value. So the absolute value of a negative number would be, it's negative, the negative of a negative. So that's just a positive number, okay? Now, this derivative right here is just the limit of this expression right here if you're looking at a very small delta t, okay? So if you imagine a very small amount of time would elapse from a particular instant, okay? So it's like, it's like in your car, your instantaneous, this would be your instantaneous rate, okay? At that particular instant, how fast is the reaction going? So it's like instantaneous speed and average speed. Okay, so like if you're traveling, if you travel, let's say 30 miles in 1 hour, you say your average speed was 30 miles per hour, right? But that doesn't mean throughout that entire trip you've been traveling at 30 miles per hour. Your actual speed during the course of your travel will depend on where you are, okay? How hard you're stepping on the gas pedal, right? So it will show up on your speedometer. Okay. Now, if P is a product, then the rate of production of P is this expression right here, dP dt, derivative of concentration of product with respect to time. That's what it's called. And the average rate is the change in the concentration of product divided by the change in concentration of time. Okay, so like I said, an expression that's written this way, d of a variable over d of another variable. That's called a derivative. That's the limit of the change of the variable on top to the change in variable at the bottom of your expression as that delta, as that denominator becomes very small. Okay. So let's look at a simple example here. Let's say the concentration of reactant A dropped from 0.100 moles per liter to 0.05 moles per liter in 5 seconds. What's the average rate of consumption of A? So what would that be? Consumption of A would be, you can say V sub A, the speed of the reaction, the rate of the reaction. In terms of the rate of consumption of A would be negative delta A, change in concentration of A. Okay, the brackets, remember, means concentration in moles per liter, right? Divided by delta T. So what's our delta A? What's the final value for concentration of A? 0.05. 0.050 moles per liter. Minus the initial value is 0.1. So 0.100 moles per liter. Divided by the amount of time that has elapsed. How much time has elapsed? 5 seconds. Okay. So what would that be? Negative, negative, so that would be negative of 0.05 minus 0.1 is negative 0.050. Okay, sig figs there. The last sig fig is the third digit after the decimal. Moles per liter divided by 5.00 seconds. So that gives you a positive number. What is 0.05 divided by 5? 0.01, right? 0.010 moles per liter per second. Okay? 2 sig figs here. 3 sig figs, so the answer should have 2 sig figs. And what's the unit for rate then? Concentration unit divided by a time unit. So it's moles per liter per second. So you can say, or you can say moles per liter per second. Okay? Or you can write it as moles per liter per second. That would be a unit of concentration, a unit of rate. Change in concentration divided by change in time. Okay, let's look at this graph here. At which time interval is the average rate of consumption of A larger? From 0 to 25 seconds. So this is typical of what you might observe when you carry out a reaction. You monitor concentration of, let's say, reactant R versus time. Okay. So what is the average rate from 0 to 25 seconds? Compare that from 25 to 50 seconds. For which time interval is the average rate of consumption of R larger? Is it in between 0 and 25, or is it between 25 and 50? Ready? 0 to 25. Okay? So what you notice typically is that, in general, the rate of a reaction slows down as it progresses. So reaction occurs, generally it will slow down. Eventually what happens to the reaction? It stops, right? So here you'll notice you went from 0.01 to 0.05 in, so here you went from 0.01 to 0.05 in 25 seconds, but this 25-second interval you just went from 0.05 to 0.025. There's a bigger change here within the same time interval as here. So you can see the steepness of your curve gives you an indication of your rate. The steeper your curve, the faster the rate. The less steep, the slower the rate. If it's flat, what does it mean? Rate is 0, right? The change in concentration is 0. So the numerator is 0. So that's how you'd interpret a curve like this. Now, what we call dRdt, the derivative of the concentration of R with respect to time, that would be the slope of the line that's tangent to your curve at any given point. That would be your instantaneous rate. Okay? The average rate would just be the difference between 2 points, the concentration between 2 points divided by the elapsed time. But for any given instant, if you want the instantaneous rate, okay, then you have to imagine from that particular point you're interested, just imagine a small, very small advancement in time and get the rate for that small advancement in time. And that's called your derivative. Okay?